All right. So I was saying that we are going to learn about stereochemistry today. And stereochemistry is is a big topic in organic chemistry. We will have a chapter, an entire chapter next semester, and it's one of the big deals in orgochem. You're gonna see why today. And so the purpose of teaching stereochem, just a little bit of it, this semester is once again to have you guys ready for next semester when we uh, discuss this learn really well. Okay, so once again, use your notebook at home. Okay, so here we have drawing a molecule here. So remember how we said in class at the very beginning that when we are drawing on paper, the flat lines means that these bonds are on the plane of the paper, in this case on the plane of the screen. The wedge bonds are coming toward you and the dashed lines are going away from you, right? So if you look at the molecule that I have here, so what I have on the right side here is blue, okay? On the left here, I have green. Coming toward me here is this point here, white. And if you guys don't say it, just let me know. And away from me here is red. Okay? And that's the first thing that I want you guys to know really well. Okay, look at the molecule. So the molecule in 3D, right? So how to translate 3D structures in the paper, okay? So once again, the molecule, so the groups that are on the plane of the screen, they are showing with flat bonds, right? So you have blue here and green here. Those are flat bonds. Coming toward me, I have here, toward me, I have white. So I'm drawing this with a wedge bond. And going away from me, I have red. So I'm going to use a dash bond for that, okay? So that's how we're going to draw these molecules. So uh, let me then introduce another idea here. So from now on, one thing that I want you guys to know is that we are going to classify organic molecules in two groups, molecules that are chirals and molecules that are achirals, okay? I'm typing on the chat. I'm going to draw it over here also. So once again, we can classify molecules into chirals and achiral, okay? And that's a big deal. We can have also, I mean, every object in nature could be classified as chiral or achiral, okay? And what's the difference between these two? Well, the first point being that a chiral molecule will not be superposable with its mirror image. Okay, that's so meaning that so a chiral molecule will never be, it's a molecule that will never be superposable with its mirror image, which basically means that these molecules can exist as enantiomers. They always will have an enantiomer, okay? Whereas achiral molecules, they don't have enantiomers because they are superposable with its mirror image. And guys, if the molecule is superposable with the mirror image, what do I mean by that? What exactly do I mean by the molecule? When you say I have a molecule which is superposable with the mirror image, what exactly does that mean? Okay, you could rotate it and it will match. So what it means basically is that if you rotate it and it matches, it basically means that it's the same molecule, right? So they don't have an enantiomer. So they're superposable with the mirror image. They don't have enantiomers. Because once again, the mirror image is superposable with the molecule, so it's the same thing. Okay, I'll give you examples now. Okay, so I want to make this first distinction So because I want you guys to learn how to classify organic molecules from now on according to uh, these groups. Okay, so we have molecules which once again could be chirals and molecules that could be achiral. So chiral molecules never superposable with their mirror images. Achiral molecules will be superposable, so it means that it's the same molecule, they just don't have enantiomers, okay? So now the next question that you will ask yourself here is, how would I know when a molecule is chiral or achiral? And you could say to me, well, I can draw the molecule, I can draw the mirror image and try to superpose it, which is fine. You could do that, but obviously sometimes that can be pretty challenging because some molecules are highly complex. And in addition to that, you need to be really good at looking pictures in 3D, molecules in 3D, in order to make sure that you don't make a mistake. So I'm gonna give you a couple of basic tools to really understand and answer this question, which is a major thing here in the class and in organic chemistry in general. So the answer to this question comes from something that we are going to call element of symmetry. Okay, meaning that what exactly do I mean by that? So what I mean is that molecules having elements of symmetry, which I show what it is now, will always be achiral. And vice versa, molecules that do not have element of symmetry will always be chiral. So I'm going to add this here. Okay. So that's the first definition. So chirality can be defined based on element. So I'm going to show you an example now. Okay, so I have a molecule here which I'm going to change. Okay, now I have two red groups here, and then white and green. Okay, so I'm going to show you. Let's define first what is an element of symmetry. So the first element of symmetry that I'm going to be presenting today here, which is the one that is mostly used in organic chemistry, is called a plane of symmetry. And the first things that we're going to do is define what this is. So a plane is, first of all, is defined by 3 points in space. Number one thing you need to know. So meaning that, so we need, if we translate this into an atoms, right? Atoms and molecules, a plane, guys, will be defined by 3 atoms, okay? For example, in this molecule, a plane could be the plane defined by this atom here, and this here, okay? This would be a plane right across here. Another plane could be this one here, and this one here. That could be a plane across this. This one here, the carbon in the center, and the white, that could be a plane right here, okay? So you can have planes everywhere in the molecule as long as you define 3 atoms. Any 3 atoms, in this case carbon atoms, will define a plane. That's the first thing you need to know, okay? So that when you think about a plane of symmetry, first you need to know what exactly is a plane, something you've seen in math, and that's once again a plane is defined by 3 atoms in a molecule. any three atoms will define a specific plane, okay? So what exactly is a plane of symmetry? The plane of symmetry is a plane which divides a molecule in two sections, one being the reflection of the second one, or the mirror image, okay? So that's the definition of a plane of symmetry, guys. A plane is defined by 3 points in space, and what exactly is a plane of symmetry? It's a plane which actually divides a molecule in two sides. One side is going to be the reflection of the other side, okay? So I'm going to show you here again this molecule. I'm going to put it next to the camera, okay? So you can see how, depending how I rotate it, I'm going to put it like this for you guys, okay? So the green is on the back, Y is coming toward you, and we have the two red. So if we if we define a plane as green, carbon, and white, so that plane here, these 3 points, that's gonna define a plane which is gonna be this, okay? This is gonna be the plane. And you can see how this plane right here, which go through, once again, green, white, and this carbon, because those are my 3 points to define a plane, you can see how this plane divides a molecule in two sections. This section to my left is actually the mirror image of the section to my right. So that's what we call a plane of symmetry. So because this molecule has a plane of symmetry, we can say that this molecule is achiral, okay? Any questions in regards to that? So I'm gonna draw this molecule now on the screen, okay, and give you achiral, right? So, and I'm going to translate what I'm doing with the molecule here with two different groups. I'm gonna draw the molecule here on the screen because at the end of the day, that's what I want you guys to do, right? So in this molecule that I have here, I got the wedge bonds. So let's do this together. So on the right side, for me, I have white. Okay, on the left side, I have green here. And then coming toward me and away from me, both are red. Okay. So if you look at the screen now, I'm gonna try to, let me see if I can make this slightly bigger. Okay. So hopefully you can see better now. So if you look at the molecule here, okay, so the plane that I was mentioning here, okay, is defined by this atom here, this carbon here, and this atom here. These three atoms are defined in the plane, and this plane in this case is exactly on the screen on your paper. That's where this plane is, okay? And that plane right here, okay, which is once again on the plane of the screen, and the plane goes through white and green, right? Divides the molecules into sections. You can see it on the screen better, the red coming toward you and the red going away from you. And one section of the molecule is a reflection of the second section. So we can classify that as a plane of symmetry. And because this molecule has a plane of symmetry, then we can say that these molecules will be achiral. And achiral molecules, once again, guys, remember, because they are achiral, they will be superposable with their mirror images, meaning that these molecules do not have enantiomers, okay? The enantiomer, what would be the enantiomer is the same molecule because they superpose with their mirror image, okay? So one of the things about that I want you guys to be really good in the class is to be able to find element of symmetries in different molecules. And the second thing that we should also be good at is to look at molecules and be able to determine if the molecules are chirals or achirals, flipping the molecules, and we are going to do this exercise now, okay? So once again, I have another molecule here. You see how this molecule have 4 different groups, right? White, red, blue, and green. And I try to find here. You can see it on the screen as well. So guys, do you see any element of symmetry in this molecule? Is there any element of symmetry in the molecule, right? There is no element of symmetry in the molecule because, no, for example, in this case, if I throw a plane of symmetry over here, defined by white, the central carbon, and blue, that divides the molecule into sections. One section is red, and the right side is blue. So they are not the same groups, right? So clearly there is no, and you can do the same for every 3 atoms defined in a plane in this molecule. So you'll see that there is no element of symmetry whatsoever here. And so we can say that the molecule is chiral, okay? So if you look at this molecule, which is chiral, you can see how the central carbon, which is the one that I'm holding here, okay, this carbon here, is bonded to 4 different groups: white, green, blue, and red. 4 different groups, okay? So any carbon, I'm gonna type it now here. So we're gonna define something called chiral center, and that's a carbon bonded to 4 different atoms or groups, okay? So any carbon, guys, bonded to 4 different atoms or groups, we will define that as a chiral center, okay? So I'm gonna give you now another trick to identify chirality. So I said, first of all, element of symmetry, you gotta find if a molecule has a plane of symmetry or not, okay? If the molecule does have a plane of symmetry, achiral. If there is no element of symmetry, it could be chiral. I'm gonna say here, sorry. Any molecule having only one chiral center, just one, will be chiral. Guys, if there is more than one chiral center, the molecule could be chiral and could be achiral. I'll show you now, okay? But if you find a molecule having only one chiral center, only one carbon bonded to 4 different atoms or groups, that molecule definitely, for sure, 100% will be chiral, meaning that it will not be superposable with its mirror image, okay? Any questions so far? So as a summary of this, once again, to repeat the ideas that we have discussed so far, we can classify molecules into chirals and achirals, okay? We are gonna use the presence of a plane of symmetry at first. I'll tell you another element of symmetry now, but at first, a plane of symmetry to determine if the molecule is chiral or achiral. Any molecule having an element of symmetry, in this case, a plane of symmetry, will be achiral, and vice versa. Molecules with no symmetry will always be achiral. I'm sorry, chiral, meaning that they can have an enantiomer, meaning that the mirror image of these chiral molecules will not be superposable, okay? And vice versa. So achiral molecules will be superposable with their mirror images, and therefore they have the same molecule, okay? Guys, let me tell you something that you might find interesting. So why is this relevant in the first place? So in chemistry and in biology in general, chirality is a big deal, okay? So let me tell you a quick example of why is that. So you have billions of proteins in your body, right? So the cells are full of proteins, and each proteins might have different functions, and that's how biology works. That's how we are alive in the first place. Every protein that you have in your body is chiral, okay? Meaning that they have a very well-defined and specific 3D structure, and they are not superposable with their mirror image, so every protein is chiral. So what happens is the following. Let's say you have a protein X, doesn't matter which one, which is because it's chiral, is going to have a very well-defined structure. So when you are sick or you have a disease and you take a drug at home, okay, these drugs are designed in such a way that they bind a specific protein, and then by binding this protein, then the drug is mainly stopping the protein function. That's more or less how they work. So let's say you have a given protein. That protein is for X reasons, let's assume it's doing something bad to you, which is causing a disease, and then you take a drug, and this drug binds this protein, block this protein from doing what it's supposed to do, and then that's how you can cure a disease, let's say. Now what happens is the following. Because the protein is chiral and it has a very well-defined structure, the molecule that you're adding, the drug that you're taking, must fit exactly in this protein pocket. So it must bind precisely to the protein. So in the past, like 50 years ago, when people in chemistry did not know much about enantiomers and chemistry in general, there was a big deal because what's the point? What's the big deal about enantiomers? And I'm going to write it over here. So enantiomers. So a chiral molecule can exist as two enantiomers, right? So enantiomers have the same, that's the whole point of this guy, same physical and chemical properties. What do I mean by that? So what I mean is I have two molecules here. Once again, I'm gonna two molecules here. One is a reflection of the second one, okay? I cannot superpose them. So two enantiomers, okay? These two guys, because they are enantiomers, they have the same physical and chemical properties, meaning that they have the same melting point, same solubility, same everything. So what I mean by that is if you are in the lab and you're doing a synthesis to make this molecule, and by any chance in the flask you have a mixture of these two, if you have these two molecules together, it would be very hard to tell that you have two molecules in the solution because they have the same physical properties. So when you measure the melting point, the solubility, and you make so many other analyses that you can do in a chemistry lab, you won't notice that there is something else because everything will show as something extremely pure. It looks like just one because they have the same melting point, the same everything. But in reality, you have two, even though you didn't notice, right? So what happened is, let's say this is a drug and you have the two enantiomers together and you don't know. So when somebody takes these two compounds and take them and they think they only have one of them is going to bind the protein that the compound is designed to bind. Whereas the second one, because it's the mirror image, it won't fit because it has a different spatial disposition. So that second one is going to be hanging in your body and might bind to some other protein and do something else. So to give you a more practical example, in 1970, there was a drug called thalidomide. You can search this in the internet. And this drug was given to women who were pregnant for dizziness and some other, uh, you know, problems that they were having during the pregnancy. So the problem was that thalidomide is a chiral molecule, and they were giving people the two enantiomers, which they didn't know. One enantiomer was doing what the drug was supposed to do, but unfortunately, the second enantiomer was actually causing some really awful side effects, and there were a lot of babies being born with birth defects. Unfortunately, and that's how they find out. What no one knew what's going on here. Why is this happening in the first place? Until they realized that in reality, thalidomide was chiral. There were two molecules that were given to these people. One of them was the good guy. The second one was causing all these birth defects. So from that point on, every drug that you can take at home, if the organic molecule, which is the active principle of the drug, if the molecule is chiral, it must be only one enantiomer, the one that they're giving you. And if they're giving you a mixture of two, they have to prove that the second enantiomer is not going to do any harm. Okay? And that's why this is so relevant. There are some other things big about stereochemistry, but just to give you the idea how this chirality thing is actually something that you experience on your daily basis whenever you take a pill at home, you know, like for example, ibuprofen is chiral and is given as a mix of enantiomers because they know the second enantiomer doesn't do any harm. Some other drugs that they're giving to people are also chirals, and they're giving us as enantiomers only if the second one is not doing any harm. Otherwise, they must only sell one pure enantiomer. And the thing is, because they have the same properties, it's extremely challenging to separate them. And it's extremely difficult to make just one. Okay, there is a whole world of organic chemistry synthesis, enantiomeric synthesis, and things like that, which are very complex. So people, this is doable, certainly, but it's very expensive. So that's why the pharma companies, when they're having chiral drugs, they are very, very careful with this. Okay. So, okay. So, Ruth, you have a question?
Yes. So, Professor, so it's very recommendable when we buy any medication, let's say any simple, let's say simple medication or anything, we have to basically focus on the chiral information, let's say, and what argument they have in case we find out that it has two
No.
chiral.
Any medication you take is approved by the FDA, which is the Federal Drug Administration. Okay. A drug cannot be given to people unless it's approved by the FDA. And developing a drug for a pharma company might take 15, 20 years. Okay, from the moment the drug is discovered to the moment that it reaches a pharmacy, it might be 20 years easily. And many of these years are spent doing all these tests with these molecules, and all the companies have to present all this data to the FDA, and the FDA decides if the drug is good enough and is safe enough that it could be given to people. So when the FDA receives an application for a drug, if they know, obviously, when they look at the structure, they know if the molecule is chiral or achiral. If the molecule is chiral, the company has to present data demonstrating that both enantiomers can be given to people. Otherwise, it's not going to be approved. So you don't need to worry about it because all is taken care of. But the pharma companies do have to take care of this, and it's a quite complex topic because once, as I said, many molecules, only one enantiomer is the one that is actually good, and it's very expensive for the companies to just make just one, because in synthesis, and you guys will learn that later, it's very easy to get both enantiomers at the same time. Okay, does that clarify your point?
Yes, thank you so much.
Okay, so guys, so that's the point about enantiomers, and that's the point about chirality. That's what we care so much. Okay, so what I want to do now is one of the things that is more challenging for you guys is to draw molecules in 3D and to learn how to determine if the molecules are chiral or achiral, okay? So here is a very simple molecule, and I'm going to ask question. Gonna make a poll here right now. So how many chiral centers? I'm gonna say one. Yes, I'm putting a question now, guys, so you can please answer the question. So how many chiral centers do you see in the molecule here? This one over here. Mhm. So definition of a chiral center, remember, any carbon bonded to 4 different atoms or groups, okay? All right, so okay, a large number of people answer one chiral center. Still a few people answer two, and very few three chiral centers. Okay, let's look at the molecule and make the analysis here. So guys, remember, this is line and angle notation, right? So this carbon, is this carbon a chiral center? You can type in the chat. Is this carbon here a chiral center? So this carbon is bonded to 3 hydrogens. So you have 3 groups that are the same, 3 hydrogens. It cannot be a chiral center. What about this carbon here? Is that a chiral center? This carbon has 2 hydrogens, same groups, not a chiral center. 3 hydrogens, not a chiral center. What about this carbon here? Is this a chiral center? It is a chiral center, right? So this molecule, by the way, guys, and I want you to also learn this, in chemistry, in organic chemistry, we label chiral centers with star, with an asterisk, okay? So I'm gonna say this is a chiral center, okay? So the molecule has one chiral center, meaning that is the molecule chiral? Can I say that the molecule is chiral? If I know that it has one chiral center, certainly the molecule indeed will be chiral, okay? So the molecule will have an enantiomer, which is not superposable with its mirror image, okay? So I'm gonna draw a second molecule now here. Okay, so a chiral center is bonded to 4 different atoms or groups, atoms or groups, okay? I wrote it in the definition. In this case, the chiral center is bonded to 2 carbons, but this carbon has 2 hydrogens and a CH3, and this carbon has 3 hydrogens, so 2 different groups. Is that clear now? Okay. So guys, I'm gonna draw a second molecule now. So I want you guys to compare these 2 molecules. I'm gonna type a question here. What is the relationship between these 2 molecules? And what I mean is, are they enantiomers? Are they different molecules? Are they the same molecule? I'm gonna So what do you think, guys? Type it in the chat. What's the relationship between these 2 guys? In the meantime, I'm gonna build a molecule here so you can see, because that's gonna help. So most people are saying they are enantiomers. Kobe said that they are the same molecule. Okay, guys, I'm gonna show you the molecule here now, all right? So I'm gonna put it like, assuming I am you guys, so I am on this, looking at the camera, right? So this could be the molecule. Actually, let me do it like this. Okay. Okay. So this molecule is the one that I'm showing on the screen. Everybody can see that. How many carbons do you have in this molecule, guys? How many carbons do you have in this molecule? 4 carbons. And you can see how the red is coming toward you. That's bromine. Does that make sense? Yes, right? Bromine coming toward you. Good. So one thing that I want to notice here, guys, is before I continue, look at the picture on the screen. There is a hydrogen behind the screen. We don't need to show it. Everybody knows that there is a hydrogen in that carbon. And everybody now knows that that carbon is actually behind the screen because the bromine is coming toward you, okay? All right, so this is the molecule, okay? Now look at what I'm gonna do, okay? So I did a flip 180 degrees. So this is, I'm gonna flip it 180 degrees. When I flip 180 degrees, where was the bromine now? Is it coming toward you or away from you? 180 flip to the right side, right? Is it the same molecule? Is this the same molecule as this one, or is it a different molecule? What do you guys think? Is this the same molecule? I'm only doing a flipping, right? So I'm not breaking any bonds, and I can flip, rotate, do whatever I want. It's always going to be the same molecule, okay? So look at the screen now, guys. One of the things that I want to really be careful when you look at this. When I look at the molecule on the left, okay, you got to look, first of all, to the zigzag pattern of the carbons, meaning that the zigzag carbon chain goes up, down, up. Whereas in the second molecule, it goes down, up, down. If I try to superpose these two to determine what they are, I can't tell because they have the zigzags in 2 different patterns. You never want that, okay? So to begin with, whenever you want to compare 2 molecules, to determine the relationship between them, you have to have both molecules on the same pattern, okay? So if I want to change the pattern on this one, what I need to do is just flip it 180 degrees. So once again, that molecule. So Jennifer is saying, but can it be read backwards? And it's the same. Jennifer, you can do whatever you want as long as you don't break any bonds and it works for you, okay? I'm giving you guys the basic tools, especially when you're learning this. You got to be very careful. Some people, so the thing about a stereochem is that different people have different skills when looking at these molecules in 3D. So for different people, different tricks are going to work differently, okay? So what I'm saying, so when you have the molecules on paper, and this is a very simple molecule, but there will be way more complex molecules. Before comparing them, make sure that they have the same carbon pattern, okay? So if I want the same carbon pattern here, what I have to do is, obviously, I have to flip the molecule horizontally 180 degrees. Okay. So if I flip 180 degrees horizontally, what I'm going to be doing is a flip. So once again, you can look at the screen now, guys. This is the molecule that you have there on the right side, right? With the bromine going away from you, right? Look at the carbon chain pattern. starting from here, down, up, down, okay? Same thing as the molecule on the right, down, up, down, with the bromine away from you. So if I flip 180 degrees, you can see now how the carbon chain pattern changed to go from down to up. So it's now going up, down, up. So that's the first thing that happens with a horizontal flip, right? It's gonna go, you're gonna flip, you're gonna change the carbon pattern up, down, up. And then obviously, if you flip 180, anything that is dash in one structure, when you flip 180, it's gonna go wedge in the second structure and vice versa, okay? So if I flip 180 to the right side, this carbon is gonna be having the bromine, obviously, and then if the bromine is dash here, the bromine is gonna be now wedge, okay? So after I did the flipping, then if I repeat the question, now what is the relationship between A and B? I'm gonna pull the question again because I really want to, so what's the relationship? Okay, so here is the question. So once again, I did the flipping, you guys got it. So what's the relationship between molecules A and B? Right, so so everybody seems to be clear. Remember when I first asked the question, 99% of you, except for Kobe, so Kobe, that was a good one, said the molecule is an enantiomer. But once we flipped, now most people realize that in reality, these two molecules are the same molecule, okay? So I'm gonna draw a different molecule here now. And I'm gonna ask another question. So what's, I'm sorry. So I want to know, I want you guys to let me know what's the relationship between B and C. So what is the relationship between molecules B and C? Some divided opinions between same and enantiomers, although most people are saying it's the same molecule. So still 24 more people to answer. Just hurry up, guys, answer the question. You can flip and rotate in any direction you want to. Doesn't matter. Just need to know what happens to every group and to the carbon chain whenever you flip the molecules, okay? So guys, Okay, so this is the molecule that I show, or actually, as a matter, sorry, not doing a good job. Here we go. Okay, so this is the molecule that I show you in the screen, right? The bromine, which is the red, is away from you, right? Is this molecule C? Everybody agrees on that? Can you guys see that? Is this molecule C? Yes, right? So this is molecule C. Why did I do now? I flip 180 vertically, right? This is C, in which the carbon pattern chain is down, up, and the bromine is away from you. That's molecule C. When I flip 180, now the carbon pattern goes up, down, and now bromine comes toward you, right? So that's a vertical flip, okay? So B and C are the same molecule, okay? So you can obviously B and A are the same. So what happened from A to C is I just did a 180 degrees flip, vertical flip. So one of the things that you gotta become good at is to be able to flip these molecules and then understand what happens after you flip the molecule. So once you're flipping either horizontally or vertically, the carbon pattern chain is going to change. And then anything that is horizontal is going to be, so is that a relationship between molecules A and C? So Tamid, A and B are the same. Is that correct? So A and C are the same as well. What happened from A to B? Horizontal flip. What happened from A to C? Vertical flip, 180 degrees. Is that clear now? Okay, so guys, you gotta be careful with that. So Ruth, what's your question?
Okay, so we are comparing B to C or A to C, I'm sorry. A to C.
A and B are the same.
Okay, and okay, yeah, I got it now. Thank you.
So these two are the same, right? We just flip this. So what happened now to make it a better picture, I'm gonna say, so what happened here from A to B is what I just did here was 180 degrees flip, horizontal. I'm gonna add this here. Okay. And from A to C is a 180 flip, vertical flipping. Both are the same molecule. The three are the same molecule, just different way of drawing them. Okay, I'm gonna draw another one now. I'm going to ask the question right now. I want to know the relationship between C and D. So what's the relationship between molecule C and molecule D? Okay, so almost 50-50 people saying that same or enantiomers. Okay, so and this is how you're gonna see why it's important. What I was saying before, if I have guys to compare these two, once again, you never want to compare pears and apples. So you want to compare the same thing. So if I take this structure here and I try to put it on top here, I can see how they don't match because the carbon chain does matches. Okay, the six that matches, but the carbon, the chiral center, do not match. One is on the second carbon and one is in the third carbon. Okay, so in order to make sure that these two obviously what's the relationship between these two, I must have not only the same carbon chain pattern but also the chiral centers being in the same position, right? And in order to do that, what I need to do right now obviously is to rotate the molecule, right? So I'm gonna take this one over here. You can flip any of them. So you're gonna pick this one on the left. You can flip the. So if I flip obviously 180 degrees vertical, I'm gonna get this. Okay. I hope everybody agrees on that. So I'm just doing a flip 180 degrees vertical, showing the molecule here, just in case you guys don't see it. So this is molecule C. Okay, the red is going away from you. If I do 180, now the carbon chain pattern is changing and then the red is going toward you. Okay, 180 flip vertically. Now you have two options. So some people, if I get these two and I put this in front of this, I can obviously see how one is the mirror image of another one. Okay, but if you are not able to see that, we can do a second flip here. In this case, we're gonna flip it 180 horizontally. And that's gonna change the carbon chain pattern, obviously. Right? So flip 180, up, down, up, that's gonna be down, up, down. And then the carbon having the bromine is gonna be this one. If the bromine was a wedge, it's gonna be dash here. And if you do that, you can see how you can superpose these two. And you can see how in one structure, so the carbon chains are matching, the chiral centers are matching, but in one molecule, the bromine is coming toward you, and in the second molecule, the bromine is going away from you. So these two are obviously enantiomers, okay? So C and D are enantiomers. Once again, you don't need to do all this flipping. Some people can say it easily, but once the moment you do this flipping, one thing that you can be good is at doing mirror image of one another. You can see how, if you put this here, you can see how these two are a mirror image of one another. And then they don't superpose, obviously. Okay. All right, guys. So continuing with these ideas, any questions so far?
Do we have class next week, by the way?
Yes, we should have class next week.
My other classes are saying that we don't have class next week, but I don't know. I'm just letting you know.
Why is that?
They said something about like a reading day or something.
Let me check right now because that's an important question. There is no reading day this semester, but I'll check very quickly in the syllabus just to make sure.
Yeah, no, I'm sure you're right. I don't know why my microbiome class is saying that there is, so I don't know.
Yeah, next week we do have a class, okay? It's Tuesday, May 17th. So, all right, guys.
Perfect.
So, let me give you another example now. There is no question. There were no questions about this. Gonna give you another example. All right, so let's look at this molecule here, and I'm gonna ask a question quickly. I'm gonna ask, yes, everything is gonna be in the final exam. So here is a question: is this molecule chiral? Okay, guys. So in the meantime, while a few people finish answering the question, I want to ask also, and you can type it on the chat, how many chiral centers do we have in this molecule? How many chiral centers? We do have very good answers, most of them 2 chiral centers. So we have a chiral center here, and we do have another chiral center. So remember how I said if we only have one chiral center, the molecule will be chiral. If there is more than one chiral center, we don't know, right? So
There's not 4 chiral centers with the carbons on the very ends.
no, this carbon has 3 hydrogens.
Oh yeah,
Same group.
about that. Yeah, my
3
bad. Sorry.
hydrogens here and 2 here, okay? So the answers actually to the question was only 50-50. Okay, guys, so because there is more than one chiral center, I need to look at the molecule and try to find a plane of symmetry, okay, to determine if the molecule is chiral or not. Is there a plane of symmetry in this molecule? So there is a plane of symmetry right here. So this plane right here, right, divides the molecules in 2 sections, one being the reflection of the second section. So there is a plane of symmetry. Therefore, the molecule is achiral. And guys, because the molecule has chiral centers and is achiral, we're gonna say that this molecule is a meso compound. Okay. So molecules having chiral centers that are achirals, we can classify them as meso compounds. Okay, I'm going to show a second molecule here. This second molecule, so I'm going to pull another question here. Is that second molecule chiral? Okay, so how many chiral centers in this molecule? Can type it on the chat, please. Once again, how many chiral centers here? So you have 2 chiral centers. Okay. Right, and then now most people luckily are getting the answer right. So is there an element of symmetry in this molecule? No chiral center, because even though these 2 groups are the same, when you put the plane here, right, one bromine is coming toward you, the second one is away from you. They are not a reflection of one another. Okay, so this molecule is indeed chiral. Now, another question that I have is, I'm gonna call this molecule A and B. Are A and B enantiomers? They are not enantiomers because they are not the mirror image of one another, right? So obviously, if you compare these 2, they are not the mirror image of one another, okay? So let's see how can we classify them. So A and B, we can say, so do they have the same molecular formula, guys? A and B. They do have the same molecular formula, right? So let me, second question is, do they have the same connectivity in between the atoms? Are the same atoms connected one to another? Same connection? They have the same connections, right? So basically every atom is connected to the same atom in each molecule. So they have the same molecular formula, they have the same connectivity. And the third question is, do they have the same spatial shape? So they don't have the same spatial disposition, because in this carbon, even though both, and this one, if you compare these 2, they are both bonded to bromine. In one of them, bromine is coming toward you. In the second one, is going away from you. So they have different orientation in space. Okay. So, guys, when we have molecules having same molecular formula, same connection, and different orientations in space, these molecules, sorry, give me 1 second. So molecules having the same molecular formula, same connection and different orientation in space, we're going to call them stereoisomers. And the name, guys, already is telling you what it is, stereoisomers. So they're isomers with different shape, with different orientation in space, okay? Now, stereoisomers can be classified into 2 groups. One of them you already know. So if 2 stereoisomers are non-superposable mirror images, how do we classify them? How do we name stereoisomers that are not superposable mirror image of one another? How do we classify them? Enantiomers. That is correct. So these are enantiomers. And remember, once again, enantiomers do have the same chemical and physical properties. And the second option is that they are simply not mirror images. So you can have stereoisomers that are non-superposable mirror images or stereoisomers that are simply not mirror images. So stereoisomers that are not mirror images, we are going to call them diastereomers. So what's the point about this? Diastereomers have different physical and chemical properties. Okay? Whereas enantiomers have the same physical and chemical properties. So it's very difficult to tell that you have a mix of enantiomers, but it's also very simple to tell that you have a mix of diastereomers because they do differ in their physical and chemical properties, okay? So let's keep that in mind. So once again, two compounds with the same molecular formula, same connection, and different orientation in space, we're gonna call them stereoisomers. And then when these stereoisomers are no superposable mirror images, we're gonna call them enantiomers. When they are simply not a mirror image of one another, we're gonna call them diastereomers. Okay. Once again, diastereomers have different physical and chemical properties, whereas enantiomers have the same physical and chemical properties. There is only one property that differs enantiomers, which is called the optical rotation. Kobe is asking, any given amount of a compound in nature world, would enantiomers and diastereomer both be present? Can you isolate one of the other? Okay, so that's an important question. A chiral molecule might have an enantiomer, but not necessarily has to exist as two enantiomers. You have chiral molecules that only one enantiomer exists. Okay, our proteins are chiral and they don't have enantiomers. So they could, but in the body, there is only one enantiomer. Okay, many of the natural products of the plants and all these compounds, they are chiral. Only one enantiomer exists. Can you isolate enantiomers from diastereomers? You can, because enantiomers and diastereomers will have different physical and chemical properties. You can also isolate diastereomers between them. Enantiomers, you can isolate enantiomers. A mix of enantiomers can be separated. In organic one, you're going to do an experiment in the lab, in organic one lab, in which you will separate two enantiomers. Okay, but it's a lot more work. It's way more complex. Okay, does that address your question, Kobe? Okay, so I'm going to draw another molecule here, guys, and I want to ask a question. That is correct for you. Thank you so much. I love that. Thank you so much. See, that I love when you guys correct me because that shows that you're paying attention. So that's good. Okay, so I'm gonna ask another question here. What's the relationship between B and C? So what's the relationship between molecule B and molecule C? Okay, so guys, if you put a meter here, what's the relationship between B and C? You can type it in the chat. They are mirror images. Can I superpose them? They don't match, right? So what's the relationship between these two? They are enantiomers. Okay, B and C are enantiomers. What is the relationship between A and C? So A and C are indeed diastereomers. So if you superpose these two, you can see how they are not the mirror image of one another. They cannot be the same compound. They have the same molecular formula, same connection, different orientation. They differ in the configuration of one carbon. This carbon here is opposite, whereas here it's the same. So they are diastereomers. So let me give you another one. Okay, so what about this, for example? I'm sorry. So diastereomers, Tamit, is two stereoisomers that are not a mirror image of one another. Okay, what are two stereoisomers? Two compounds with the same molecular formula, same connectivity, different orientation in space. That's stereoisomers. When they are not the mirror image of one another, diastereomers. These two, they have same molecular formula, same connection, different orientation in space here and here. Not a mirror image, diastereomers. Okay. Guys, what's the relationship between A and D? So A and D obviously are the same, right? What happened from A to D? 180 degrees horizontal flip, okay? All right, so I'm gonna give you another example now. Um, okay, so how many chiral centers here in this molecule? How many chiral centers in that molecule? 2 chiral centers, so that is correct. Okay, I'm gonna draw another molecule here now. So what is the relationship between these two? So I'm gonna say this is A and this is B. I'm gonna ask a question. Give you a couple of minutes for you to think about it. So what is the relationship between A and B, guys? Okay. Thirty people are still to answer. Just answer the question as soon as you can, please. All right, so most people got it right. So A and B are obviously the same. So anybody can type on the chat what happened from A to B. Why did I do from A to B? So we did a flipping, horizontal flipping in 180 degrees. So that is correct. So what about A and C, guys? What's the relationship between A and C? So just, you have the question on the poll, just please answer the question. Okay. Okay, guys, there's few people taking longer, so just finish the answering the question. So, um, so A and C are the same. So can anybody type on the chat what happened from A to C? What did I do from A to C? So we did a 180 vertical flip, okay? So 180 vertical flip. When you do a vertical flip, you change the carbon chain pattern. Anything that is wedged is going to be dashed and vice versa, okay? So guys, what is the relationship between A and D? So what's the relationship between A and D? But you can do whatever you want. I mean, you can rotate it however you want to compare them. It's pretty divided so far, almost 50-50, okay? Okay, guys, so most people answer diastereomers, okay? Almost twice, actually. That is run. So A and D are enantiomers, okay? Let me show you. So if you take a structure D, and you put it on top of A, so this is a trick I'm gonna show you guys, okay? You know how the carbon chain pattern is the same, up, down, up, down. That matches well. The connection also matches, so this carbon connected to the bromine and the carbon connected to the chlorine are also matching. So you gotta make the match with the carbon chain and the connections, okay? They are stereoisomers. And once I have that, I can see that this connection here are opposite. One is coming toward me, the second one is away from me, and these two connections are also opposite, away and toward me, okay? So, guys, when you have something that is opposite configuration, away toward, once you superpose, that's clearly a mirror image, okay? So these two are enantiomers. So you could also do this the following. You can rotate this, and I'm gonna do it for those who might have a problem. So I'm gonna do a 180 degrees horizontal flip in case you guys need to see that. So if I do, sorry, a 180 horizontal flip, the carbon chain is gonna be this, right? And then the chlorine is gonna be at this position. If it's wedge here, it's gonna be dash. And the bromine is gonna be at this position. If it's wedge here, it will be, I'm sorry, if it's dash here, it will be wedge here. So that's 180 horizontal flip. And guys, if you put this next to one another, you can see how they are perfect mirror image of one another, okay? And they're not superposable. Is there any element of symmetry in this molecule? Clearly not, so the molecule is chiral, right? So you gotta think about all these things. Is the molecule chiral? Yes. If it's chiral, it will have an enantiomer. It will not be superposable with its enantiomer. And then what's the enantiomer? So what's the mirror image? The mirror image is this. So clearly the relationship between these two are enantiomers. Again, if the configuration, so if the orientation of one carbon is opposite and on the other carbon as well, there will be an enantiomer. So if you have 4 chiral centers and the 4 chiral centers have the opposite orientation in the other molecule, the 4 of them, the 2 molecules will be enantiomers, okay? What about this one? Again, if anybody has a question, feel free to type it on the chat or raise your hand, okay? This is going to be molecule E, and I'm going to type a question right now. I'm going to poll a question for you guys, which is going to be the relationship between A and E. Want to know the relationship between A and E? Okay, so a large number of people, that's very good to see, answer the question correctly. So A and E are diastereomers. So once again, guys, if I try to superpose molecule E on top of A, look at this. And this is for those of you who are having a hard time looking into this, and even if you're doing okay, always good to recheck. Okay, I cannot superpose these two because even though the carbon chain matches, the connection does not match. So this carbon is connected to the chlorine, whereas in the structure A is connected to bromine. So to compare these two, I need to do a flipping, okay? Because I do want to match perfectly fine, not only the carbon chain, but also the connectivity. So if I do 180-degree flipping to the right side, the bromine is going to be now in this position and it's going to be going dash, and chlorine will be in this position and will be going dash. So I'm going to write bromine here, and I'm going to write chlorine here, okay? Now, after I flipped, if I try to superpose, I can see now the carbon chain matches, the connection also matches. This carbon is bonded to bromine in both cases, and this one to chlorine. When I try to superpose, I can see that these two here, they match. So they have the same configuration on the carbon, same orientation here, but here they have opposite orientation. So when you have more than one chiral center, obviously, if the difference is in one, or at least one of them is the same and the rest are different, obviously they will be diastereomers, okay? So A, I'm gonna write it over here, A and E are diastereomers. And I'm gonna give you a last example. So this is gonna be F. And I want to know, I'm gonna update the question, the relationship between E and F. So remember, guys, when you compare two structures, first make sure the carbon pattern chain matches. Second, make sure the connection matches. Put one on top of the other one, then you can reach a conclusion of the relationship. So I can see, like, even though some people are still made a mistake, a large number of people answer correctly. So once again, if I try to superpose this here, the carbon zigzag matches, but the connection does not. because this one is connected to bromine and they're here to chlorine, and same thing over here. So what I need to do, once again, I need to do a flip. And once I do the flipping, I will be able to superpose these two structures, okay? So once I do the 180-degree flipping horizontal, obviously bromine, which is here, is going to be coming here, and now it's going to be wedged. Chlorine, which is here, is going to be coming here, and now it's going to be wedged as well. So this is going to be bromine, it's going to be chlorine. And now if I try to superpose these two, I can see how the carbon matches, the connection matches, and both chiral centers are opposite. This one is opposite of this one. This one is opposite of this one. If both chiral centers are opposite, the relationship is enantiomers, okay? So I'm going to say that E and F are enantiomers. So guys, the bottom line is to compare two structures, make sure that the carbon pattern chain matches. Make sure that the connection matches. Then superpose them. If every chiral center is the opposite to one another, they will be two enantiomers. Okay? If one chiral center is the same, everything else is different, or two are the same, but at least if one is different and everything else is the same, they will be diastereomers. Okay? All right, guys. So with this, I'm gonna end today's class. I'm gonna stop recording. So